Okay, good morning, everyone. It's my great pleasure to introduce our second speaker today, Professor Cheng from Hong Kong University of Science and Technology. Tim, he got his bachelor degree from National Taiwan University in Taiwan and a PhD from UC Berkeley. That was in 1988. And he joined AT&T Bell Lab for 5 years. And in 1993, he joined the faculty of UC Santa Barbara, and where he has done so many things and published so many papers. Yeah, he was the founding director for UCSB Computer Engineering program, and also served as a department chair. And let me just mention one thing. His actual mutual funding was more than 200 million US dollars. I think that's a big amount. Yeah. And in 2016, he was recruited by Hong Kong University of Science and Technology as the Dean of Engineering, in concurrence with chair professor in ECE and CSE, Computer Science and Engineering. And just this year, he was appointed as the Vice President for Research and Development. And I guess you all know that he has done a lot of research in various areas. You all know that he has done published many papers in computer engineering, in field site testing and design verification. He also covered research area in computer vision, medical image analysis, and even some software and electronics. He has published more than 500 papers, and he got the 12th Best Paper Award from top conference and journals. Yeah, he is IEEE Fellow. And today he is going to give us a shorter title. He's going to give us a talk on AI accelerator with ultra low power and computing in memory. And yeah, you look at the title here. There's ultra low power AI accelerator or AIoT, heterogeneous integration, almost everything. So let's welcome Cheng.
Thank you, KJ, for the introduction. I'm really pleased to be able to come here today. I've been attending ITC regularly until I moved to Hong Kong, which was 6.5 years ago. And I appreciate the invitation. And today I'm going to talk about AI accelerators. And here the keywords are computing memory, co-design, and heterogeneous integration. I always like to use the background of our campus as my title slide, which right next to Pacific Ocean. That's what I see from my office. Not just my office, almost all faculty members' office get this view. Which remind me of my UC Santa Barbara day, which is happened to be right next to Pacific Ocean too. We have seen tremendous explosion in AI, and we experienced this wave of AI revolution. And many applications become real, from transportation, fintech, medicine, healthcare to education. All those are supported by AI infrastructures in the forms of algorithms like machine learning to computer vision, natural language processing. But there's no question such progress has been driven at least to the great extent by the advances in AI hardware. Many people actually complain that hardware people hasn't been able to get sufficient credit for this AI revolution. And moving forward, there's no question there's still more application to be seen, which are captured by data. And infrastructure in algorithms, we need to have more complicated algorithms to keep up. So increasingly, people worry about the computing power is the bottleneck. So these three elements, data, algorithm, and computing power, are three key elements for driving AI. And the first two, no question, we see the pathway to grow. So that creates tremendous challenge as well as huge opportunity for advancing computing power. These data come from OpenAI, which show the compute usage of the largest AI system over the past 60 years, back to 1960s. The vertical axis is roughly the computing power times days. So petaflops times days for training the largest AI system of that year. And you can clearly see a very distinct two eras. Before 2012, where the modern deep learning spurs AlexNet, the growth rate of this compute usage is about following the Moore's law, 2 years doubling, equivalent to 1.4x per year's growth. But in the past 10 years, it doubled every 3.4 months, which is equivalent to 10x per year. But then you look at general purpose computing, CPU, GPU, this is a slide directly copied from NVIDIA, even though there are two curves, but pretty much it's 1.x per year. And I just show you that the demand we have seen in the past 10 years is 10x per year. No wonder we're buying more and more GPUs. I count my students. Per student, I need to buy 4 GPU cards for them, which is buying computer never seen as a central research facility for university, but today it become the most expensive central research facility for university. Everyone's buying more GPU. AMD and NVIDIA are doing very well. Another angle to look at the revolution of AI is, which is not new, means most people agree, for 40 years, even neural network. But the increase of the accuracy, which show in the chart, is getting flatter and flatter with respect to the amount of computing resources, energy consumption required. We still have tremendous room for improving the intelligence or AI accuracy, but per unit increase will incur enormous amount of hardware resources and memory. This is not sustainable. And we must change the curve, means every unit of increase of accuracy or intelligence must come with much more manageable amount of extra resources. And the way to do it is to better match the AI hardware to the computational characteristics of AI. So this shows the AI value chain from hardware to applications. Most left part is manufacturing, right most is the software application, the solution. And we have seen the explosive growth in solutions of applications, which are very fragmented. That's the rightmost part of the chart. And earlier I mentioned that general purpose computing platform, CPU, GPU, will not be able to keep up. That created this ASIC or AI accelerator domain, which we have seen many startups as well as giants doing this. For example, DJI, which is a drone company, happened to be a spin-off from our university. All the Hollywood movie you have seen that they're shooting use DJI drone. They designed their own chips, ASIC, for computer vision, used for drone. They're not selling their chips. And not to mention that the self-driving car, all they're designing their ASIC particularly for their application. So all these accelerators are in strong domain and actually are companion the general purpose platform, the CPU and GPU. Moving forward, there's no question everyone can see Our society has ubiquitous AI everywhere, in sensors, everything. But it's not there because of hardware limitation, I would say. We don't have a shortage of data. We don't have intelligent people to design algorithms to keep up with those data. We have shortage of hardware. So we must improve AI hardware performance and energy efficiency, not by multiple times, by multiple orders of magnitude. Whoever can do it, you don't see the limitation in the application. But all this somewhat has to be customized because general platform can only do things to the extent they can do. Therefore, customization cannot require hundreds of designers, years of time to complete. So design productivity and time to market is crucial. That's where the EDA tools play a critical role. All this will make only if you only require tens of engineers and quarters of time, several months of time to complete a custom chip, especially for the inference market, AIoT domain. So with this, a few years ago, we established a new center called AI Chip Center for Emerging Smart Systems, funded by Hong Kong government, roughly over 440 million Hong Kong dollars. It's established an international center. Idea is led by our university, also together with Stanford, Notre Dame, ETH, and EPFL. Not only that, we hire a lot of engineers full-time into the center who have tape-out experience, who have algorithm experience, who have application experience, doing the vertical integration, building a team. Our key strategy, there are many things to do, but I will highlight the key technical strategies are these 4 points. First is integrating emerging technology with or into silicon CMOS chips. This big data era, so emerging memories such as RAM, MRAMs are a key element, and they must integrate with the silicon. Silicon photonics is also important, and all these processes are not compatible, so heterogeneous integration, 3D IC is a must. Second bullet is architecture research. I think with big data era, all the architecture must be memory-centric instead of compute-centric. The third one is EDA for AI design automation, which I mentioned earlier. Not only that, there are also a lot of EDA problems can take advantage of new advances in AI. So we call AI for EDA, EDA for AI. And finally is application, algorithm, and hardware co-design, co-optimization. I will illustrate using the animation here. So today, mostly we still implement the AI or machine learning algorithm, writing Python or C++, use CUDA, compile that into the general purpose platform. So you have two distinct color software running on general purpose hardware. AI acceleration is ASIC concept, or at least domain-specific concept that you customize your hardware to better match your algorithm, which give you arguably maybe 10x plus potential improvement for energy and the performance improvement. Likewise, algorithms have many ways to do it. So understanding the hardware, know the limitation, you can then adapt the software and algorithm to your hardware. So this iterative customization and adaptation will give you additional opportunity for further optimization. So use the chart I showed at the very beginning, the 3-layer application infrastructure to hardware. Instead of running on general purpose CPU, GPU platform, this co-design concept is producing the computer vision accelerator, machine learning accelerator, natural language accelerator that captured by this colored shapes. And this co-design, co-optimization concept give you the opportunity for optimization that otherwise general purpose platform would not be able to offer. And this concept has been booming for the past 5-7 years, this specialized AI accelerator. If you look at the name, you pretty much can find all these A to Z processing units. You heard CPU, GPU, and Google's TPU, and the GraphCore Core IPU, and you have vision processing units. Pretty much everything you can see. In many ways, they are customized for their own domain, but in many ways, they are similar because, like previous John's talk, metrics multiplication, for example, is very common. Everybody needs to accelerate it. So to show all these domain-specific processors, how much they can contribute, I took this latest, I think a couple months ago, IEEE Spectrum published this data ML Perf, which is the Olympics of machine learning. It's started about 3.5 years ago, consisting of 8 benchmark tests covering image recognition, medical image analysis, segmentation, to reinforcement learning, natural language processing, etc. These are the standard benchmark tests. The chart basically have 4 curves. The lowest curve is referring to the Moore's law. If you just look at what every doubling every 2 years, that's you can see the intersection of under December 20s is 2x. But then for this benchmark training performance, you can see they really outpace the Moore's law. That comes from the architecture and the code design advantages, not from the hardware devices alone, which is very encouraging. And that means, for example, this year, the performance is 10x better than Moore's law can already offer in terms of training performance for this benchmark. And I take one of the 8 benchmarks I show in the table. I apologize, it's too small. This is a benchmark of BERT. This is a transformer-based machine learning technique for natural language processing. And you see many rows there. The first one is a single accelerator based on NVIDIA A100. It takes 255 minutes. But then if you look at the core, for example, you can see GraphCore's IPU. If you use 256 of that, you reduce that time to 3.19 minutes. And if you use Google's TPU V4 with 4K accelerators, it's reduced to 0.18 minutes. So this enormous range of acceleration you can achieve for training. But we don't end there. You see, the AI's 3 elements of driving forces: data, algorithm, and hardware or computing power. Earlier I showed if you combine co-design of algorithm with hardware, you accomplish what we show there. But for AIoT, for edge device, very often they have a target application. An application generate data are labeled. So if you co-optimize data, algorithm, and hardware together, and following what I showed, conceptually what I showed earlier through customization and adaptation iteratively, to some extent is design space exploration across all 3 layers. And conceptually, that what you're going to do is design the specialized hardware like we have seen across application infrastructure to hardware. And we strongly believe this is the way to go, because if you look at the embedded intelligence for AIoT, the demand for greater functionality, the demand for lighter weight, lower power, with very high accuracy, nothing can be compromised, because if you don't get enough high accuracy, people are not using it. And many of those are vision-driven, speech-driven. Those are real-time data coming in. You don't have time to really send it out. So the text here basically showing we find the embedded intelligence for AIoT require extra lightweight, very low power, high accuracy, and the real-time performance. And the way to do is a cross-layer code design. And 3 years ago, we started this project. I'll give you an example, this intelligent camera for head counting. It's just a driver example to show you the idea. We designed a very low power image sensor several years ago. It's running at microwatt and being able to do some simple image, the motion sensing. The array size is not big, 256 by 216. So it's not for human visualization. It's more for autonomous detection. So if we can design a ultra low power neural network for head counting, head counting is not very complicated. Today, if you send it to server or cloud, you can do that easily. You keep streaming the video to the cloud to get how many people in. But now you want to include that intelligence in the sensor right next to the image sensor. If you can drop that in front of the conference room or put that in front of the elevator and use a coin battery, last the entire span of the product cycle, drop and play. And you can imagine there are many products like that. And today, if we put that in front of the entrance of the conference room, how many people coming in, how many going out at any single moment in this room can be captured. So design this intelligent people counting neural network require neural network search, then compress your model, and the co-design with the special hardware. And we did that. And just show you the demo that this is not actually facial recognition. It's basically on top of the person coming into the room, then two coming in, one going out, so you know one person in that room. And we designed the accelerator game to have a reconfigurable resolution that, neural networks, some of the layer need 8 bits, some of the layer need 2 bits resolution. And all this is software to optimize it. Without getting into detail, that using that as a driver, we develop a detour chain. And a lot of modules are reusable. Because if it's convolutional neural network based or transformer based, the building blocks are very similar. So for any new application comes in, which represent by data, could be text, could be image, could be audio, could be video, could be time series data like your ECG or EMG, then the tool flow will be able to optimize it, compress it, find the best network to search, and to produce a semi-automatically tailor-made AI accelerator. So each one is only tailored for that application, but there are a lot of building blocks are very similar. And the design space exploration tool is highly reusable. So I'm looking at the time. Here, I summarize some key architecture strategies use AI acceleration. That this idea primarily focus on neural network-based accelerator. Earlier, I mentioned the first bullet is application, machine learning algorithm, and architecture code design. The second bullet is that there's a clear trend for deep neural network. It's especially for inference, you try to minimize or eliminate floating point calculation and use fixed point calculation as much feasible. Also, it has been shown analog computing is much more energy efficient than digital computing for deep neural network. The reason is simple. A lot of metric application, you multiply a lot of numbers together, you sum them together. You can tolerate errors. Once you can tolerate error, analog computing has tremendous advantage. And following that, a lot of people exploring the mixed data precision, not only from floating point to fixed point, from fixed point, from 16-bit to 8-bit, 8-bit to 4-bit, 4-bit to 2-bit to binary. And different layer of your neural network can have a different bit precision. Which layer more important, which channel are more important, you need tool to evaluate it. And that's EDA issue. And the next bullet is near and in-memory computing. We have seen a lot of research based on SRAMs, a lot of research based on RAM. I will touch on this topic a little bit more detail later, which primarily addressing the von Neumann bottleneck, the memory wall problem. So because of this trend, we see the growing use of emerging non-volatile memory, such as RAM, resistance RAM, and some people exploring MRAM as well. Most of the deep neural network, whether it's convolution, CNN-based, RNN-based, or transformer-based, I think metric multiplication is still the dominating part. So exploring sparsity and exploring data arrangement has been researched to death, I would say. I think John's talk earlier also would touch upon this topic. So this a little bit more detailed computing memory, which is addressing the memory wall problem. There are two camps. One is called analog computing memory. The other camp is working on digital version. So if you look at the three charts here that start with the left-hand one, a lot of this CIM is primarily focusing on MAC, multiply and accumulate. So it's not general computing. Sometimes people say, well, how can you put compute totally in memory? That's not the intention. It's a limited type of computing in memory. And the bottleneck is in memory I/O. So the center one, the idea is, can we do analog multiply and accumulate completely in memory, which is the intention. And interface with the rest of the system through DAC and ADC. So in short is, in the sub-bullet here, under the second bullet is, the system is DAC, followed by analog MAC in memory, followed by ADC. And there's advantages as well as problems with analog CIM. It's noisy, a lot of variations. So there's another camp trying to do digital CIM, particularly SRAM based. Why don't we have been using registers in logic, right? But register is too expensive, too energy consuming, and not enough. Then why don't you pack enough SRAM together with logic? Process-wise, they can be made compatible. So you just have those building blocks with memory and the logic all together. So the data flow become very smooth through the system without transfer the data out of the memory. So it's a little logic, huge memory. That's another direction people are exploring. So I'd like to focus a little bit about RAM-based in-memory computing, RAM CIM, which our center has been spending a lot of time working on this area. So to illustrate that, maybe focus on the top right corner chart. The idea is that if you want to do multiplication, you have a multiplicand times multiplier. And multiplier, why don't you program the RAM and use the conductance or the inverse of a resistance to represent the value of the multiplier. And the multiplicand represent by voltage. Then the current flows through the resistors, through the memristors. It's a multiplication. Then how to do accumulation? Since the value is represented by current, signing current together is very simple, wire them together. So this column, if I have an array of n elements like this, then my input vector represents as a voltage, my multiplier vector represents as a conductance, which I programmed my memristor to. Then the current at the output is MAC of the two multiplication, inner product of these two vectors. If I extend this to array, then I can do multiplication in one shot. So you can see, since I need to program the memristors into specific value, this is analog, and the voltage is analog, current is analog. So this is the center point of a lot of research on RM-based CIM. There is another category of CIM is implementing CAM, content addressable memory or associated memory. This is representing the bottom right corner. It's RM-based, is used for pattern matching. Why RN? RN has the advantage of a very high density. It's passive element. So you can build multiple layers of that with low energy, and it's non-volatile. And this is analog computing, as I mentioned earlier. So for CNN, RNN, or transformer, if you look at all the AI machine learning algorithm, huge amount of calculation can be narrowed down in as matrix multiplication, I show in the left-hand side. So what you want to do is build a very efficient dot product engine, and inside this RN array, you program each element conductance to reflect the G, the metric value. And you build peripheral circuitry so that when vector comes in, you convert that into voltage, and the output at the represented as N would be the output vector. And all this is in one cycle instead of multiply and accumulate. And this array, how big you want to be? Thousands by thousands. So with that, in the past decade, starting about early 2012, 2013, people start building this 3D memristor array from industry, from university. Some of them are building 2-3 layers of RM, and the largest I have seen experimentally is 8 layers of RM on top of CMOS. Another thing is architecture. Some are called 1T1R. It's like a random DRAM and SRAM. You need to have access transistor to connect to every R memristor. But people also talking about 1TNR. You use a crossbar structure. So you use transistor only to access the entire column or entire row. There are a wide range of research on that. This table, I'm not going to get into detail, but if you look at the last row, the references, the work starts from 2012 all the way to today. The capacity varies. The switching material memristors, wide range. Oxide base is still the most popular one. And the other one is electrode metal. There are different kind of material. But once you build such an array, a CMOS on top of that, you grow RM array. That's heterogeneous integration. You need to build peripheral circuitry to do those AD conversion, to do current sensing, etc. So we have seen also a lot of progress based on this RM technology to offer computing memory macro, which I mentioned earlier to do. To exactly doing this. This is conjecture diagram. You imagine that you have RM, multiple layer RM implementing this. And you need to have a peripheral circuit to facilitate all this MAC operation. Yep. Sorry. So starting about 2014, 2015, we start seeing those analog computing memory macro based on RM published in various places. Again, it's a very busy chart, but the purpose to show the progress. Technology now, we have seen 22 nanometer and the 40 nanometer implementation. The last row show, again, where they publish. For example, the latest one, That is to in ITC and the general solid-state circuit, they're able to implement multiple megabits of RAM, implementing, for example, mobile net, VGG16, and conducting tasks such like ImageNet. Enormous progress in the past 6-7 years. But this is still not quite in production. I think TSMC has embedded RAM as a memory, but they still don't offer this CIM as a macro for all this CIM still in prototyping demonstration stage. Why? There are enormous variations for those devices. I think this community know variation very well. For RAM memristor, which is the basic of RAM, is two-terminal device, switching material sandwiched between two electrodes. The chart here is IV curve. You apply voltage, sense the current, and there are two states. The slope basically represents the state, high resistance or low resistance. But what happened is, if you build large number of them in large array, and you try to sweep the device, you will find that they shift to the right, shift to the left. And for the same device, if you sweep it multiple times, it shifts as well. So for this particular case, we tried 6 devices. Then many years ago, I think 5 years ago, 6 devices, and each one we sweep 4 times. There are 24 curves there. You can see significant variation. When you want to use a device, for example, we said this is a conceptual diagram. The device is a resistor. You apply voltage, measure the current as a state. Since you want to maintain low power, so the read voltage is much small, typically this range. So in the inset you find here, the slope represents 2 different states, high and low, right? And you can notice they're all over the place. It means there is a very high error rate. It's difficult to control. How to address this problem? Because you need to use this. Either it's a binary memory element, you already have an issue. High and low, sometimes a bit error rate. Not to mention you want to use it as an analog element with wide range of resistance. If you want to have a 4 bits information for one resistor, you need 16 different levels. Now you can imagine how difficult to control it. So without getting into too much detail, I want to just highlight a few directions people have been looking at. The first one is, say, we recognize that when you train a neural network, eventually you want to program the weight. You accept the reality that the way you're going to program the device will vary, will not be perfect. So how about take that variation into account when you train the neural network? And that becomes this noise aware or the device variation aware training for neural network. A lot of work along this direction, people find that if you take that factor into account in the training phase, your overall accuracy will be much robust, even in the presence of variance. That's one direction people are looking into. Another direction is due compensation. After you program your weights in RAM, you conduct a characterization phase. You read it back and you know what's the range, how much it deviates. Then you do one extra step called compensation through adding off shift. You add what extra row or extra column to allow you to per row, per column offset to minimize the error. And it's also shown to be effective. And the third one I want to mention for this community, a lot of people are familiar with ECC, error correction code. And now you use RAM as a memory. We need not only digital ECC, we need analog ECC. which means the code you created, if the value, analog value, is slightly deviate from the target value, you still consider that valid. But if there's a fatal error, like stuck at 1 or stuck at 0, you need to detect your analog ACC. So a lot of interesting work along that direction. And you can extend this for CAN, content addressable memory, usually used for digital pattern recognition. But a lot of AI work require analog matching, means each value, if fall within a range, you consider a match. If fall outside the range, is mismatch. How will you be able to design an analog content addressable memory based on RAM to match range of values for a vector? If each element in your vector match the range, it's a hit. And that has tremendous value for AI. And final point is ratio-based encoding, which is some work we did in the past several years. I want to mention that in a few minutes, spend 2-3 minutes before I conclude my talk. Let's first review the traditional way of RM. Is you use a programmable resistor as a memory element, and you apply voltage and sense the current as a state, which I mentioned earlier. There's tremendous variation. Now, how about we use 2 of them instead of just 1? We recognize the device is very lousy. You cannot trust them too much. You cannot control it too well. So you put 2 of them together in series. And also, instead of sensing the current, you sense the voltage in the middle. So consider you want to use this to store 2 state, 1 or 0. And you program that as high resistance, low resistance to represent one logic value. And the opposite is another logic value. So in other words, the state is the ratio of R2 versus the sum of this resistor. And remember, R1, R2 are supposed to be very different, like on-off ratio could be 100. Therefore, this voltage, this state would be very close to 1 or very close to 0. So suddenly, even though the device is very lousy, the memory element becomes very robust. The only way to flip it is the target high resistance state happen to be lower than the target low resistance state. And that probability is not very high. If you don't believe in it, bear with me. I use some mathematics to show you why this works. Again, start with the traditional one. Resistor, use current sensing. You apply V-read. And what let's say, use this resistor to represent 2 states. High resistance state is 100 kmol, low resistance is 1 k ohm. And because it's variation, so you represent the actual resistance as a random variable, which I have shown here in the table. To determine its logic value, you use the threshold voltage in between. I separate these 2. So the bottom curve here showing that in this particular example, if you use the middle voltage or middle resistance as a threshold, the bit error is 10 to the minus 3. Now, if you can improve your device, which the community have been trying to do, a lot of a new device coming out, which means the shape of the random distribution becomes sharper, but effectively is the bit error will reduce because the device improve. Now you use this ratio-based idea. So in the right-hand side, which the state represent as the ratio of R1, R2 divided by R1 plus R2. We use the exact same distribution, device distribution in the left. And now you see the state is now normalized between 0 and 1. If you use the random variable analysis, you will find that the two distribution becomes so separated, like we show here. And you use the central voltage, you find that with these two devices with exactly the same quality as the left-hand side one, the bit error rate improved by 100x. Not only that, if the device get better, corresponding to the red curve in the left, the improvement is even greater. In this case, improved from 100x to 1000x. So that is a perfect example of using an architecture solution to complement device limitation. I think our community has been doing that for the past tens of years. So next question is, can we extend this idea to multi-level cell? Because we talk about here it's only binary. The answer is yes. If your memristor can be programmed into 3 bits, 4 bit, the same idea can apply to dramatically improve the robustness of your analog memristor. The causes, instead of using 1 R, you use 2 R. Instead of current sensing, you use voltage sensing. So I know KJ is looking at me. My time is running up. So I want to summarize. I believe there are several continuing trends creating huge opportunity for AI hardware. The first one is we don't see the stop of data explosion. We don't have shortage of that. We don't have shortage of label data. And the algorithm continue to get more complicated. That means we drive the better hardware. And we also see strong demand and the clear benefits of moving AI computing and intelligence from cloud and servers to edge device. Because especially for vision, for video, audio data, the demand is so significant. Reducing the communication cost, embedded intelligence into AIoT, no question is the way to go. I see that in MRI machine, CT machine, huge amount of data, and they are very reluctant to transfer that data to cloud. The second bullet is custom-made chips fitting application going mainstream. It's not only for efficiency. I think embedding your company's value inside your chips becoming a necessity for product differentiation. We saw a lot of application and the solution company. They have been using MCU or general purpose platform and keep their value in software. But increasingly, they like that software to tie into their hardware. And we saw that Apple started 15 years ago. Self-driving car all have their own customized hardware. And they're not going to sell their custom chip. Their custom chips are only to support their own business. And another key point is many of those chips may not need the most advanced manufacturing because architecture, application, software advantages are value. So as long as it's not a too old manufacturing technology node, that should be okay from cost point of view. So to support AIoT with energy efficiency, high accuracy, and the real-time embedded intelligence, we believe application-specific code design is an important solution, and for which the EDA architecture and all the verification test community will play a very important role. So I conclude my talk here. Do we have time to take a couple questions?
Yeah, I think since we have run out of time, maybe we can take at most one question.
I see a gentleman here.
Okay, team, this is Stefan, your ex-colleague at Bell Labs. How are you?
Great.
Fantastic performance. My question to you is based on your conclusions here. It's a great directions. Now, when these AI-based applications would be cost-effective to be used in the edge devices, Apple's devices are not cost-effective solution. This is too expensive.
Yes.
So to make it more pervasive use in the whole society, in the whole world, it has to be cost-effective.
Yes.
Is this a semiconductor technology or new architecture or everything together? What is it?
Excellent question. I think what I saw is evolution of phases. Many solution and application company, they already have a high value profit margin in their application domain. And they are driving application-specific IC to support their business as a product differentiation. So the first phase, at least my interaction with many companies, they're interested in working with us is product differentiation. But because of this domain solution are very marginalized, reusable. So there's a belief moving forward, once the deployment is there, the cost will continue to go down. So it's not the other way around. You have to capture or trigger by low-cost solution to start with. If that's the case, I think it will be very difficult. And we see not only tens, hundreds of companies have customer, have huge product margin, want to design their own chips. And most importantly, they are not selling their chips. This is very interesting trend, different from what we have seen in the ASIC market in the past, which you need to have hundreds of customers, otherwise you cannot survive. Now is you design your own, then I think the infrastructure will gradually become more mature. That's my personal view. I don't know whether I answer your question.
No, sure. But what I'm not contradicting, however, asking more question on your second bullet item.
Mm-hmm.
Don't you think standard solutions take it to more economic solution rather than a custom made really with something? That's almost like holding the market power and not sharing with anybody.
Yes, definitely certain. So it's still probably in a domain specific area, not application specific area. So some standardization is definitely the way to go. It's when that's going to happen. All right, now I'm running out of time, I guess.
Yeah. So, sorry, I think we need to close this session. But I think next will be the coffee break. So if you have any further question, you can ask him during the break. Okay. So
Thank you.
Let's thank Tim again.